For this video, we're going to be discussing scatter plots and lines of best fit. So let's start by talking about what a scatter plot is. A scatter plot is just a type of graph comparing two sets of data. One set of data is represented by the x-axis, and one is by the y-axis. And the points are put together on the graph comparing the x and y data. So, in case you forgot what exactly that means, let's say I gave you a table, and I said, here's my x data, here's my y data. Let's just say this is 1, 2, 2, 3, and 3, 4. Well, my scatter plot is simply plotting those pieces of data. Alright, this is my x, this is my y, and I just want to plot my data. 1, 2, 2, 3, 3, 4. Alright, that's all we're doing for a scatter plot, is we're plotting one set of data is for x, one set of data is for y. Now we're going to be doing these for word problems, so it's not going to necessarily tell us this is the x, this is the y. We're going to need to figure that out for ourselves. But it is pretty much that simple when we're making a scatter plot. So here's example 1. It says create a scatter plot for the given data. So we have the number of hours of sleep that a student gets and their score on the test. So my first step is I want to set up my x and y axes. All right? So what I'm going to say is my y-axis over here, that's going to be their test score. And then on the bottom here, this is going to be, I'll shrink this down a little. My x-axis down here, this is going to be the hours of sleep. And I don't really have a whole lot of room to label these. When you do this in class, I'm going to expect you to label both the x and the y. So test score, hours of sleep. And then all I need to do now is I'm going to take my pairs of data, 9 and 93, 5 and 70, 6 and 77, 6 and 81, 8 and 88, 9 and 91, 10 and 76, 7 and 78, 6 and 68, and 8 and 100. I'm going to take those pieces of paired data, and all I'm going to do is I'm going to plot them. Oh, grab the wrong thing. I'm just going to plot them on my graph, and there we go. Now I've got a scatter plot. All I did is I took each one of these pairs of data, an x and a y, and I plotted them on my coordinate plane here. So here I've got 5 and 70. I've got 6 and what is this? 68. Here's 6 and 77. All right. I don't know what this one is. Oh, 6 and 81. Then over here I've got 7 and 78. Over here I've got 8 and 88 and 8 and 100. I've got 9 and 93. Or 9 and 91 and 9 and 93, and then all the way over here, I've got 10 and 76. So altogether, these make up a scatter plot. So making a scatter plot's no big deal. It's just graphing ordered pairs. Now, correlation, right? This is something that might be new, and this is what we really want to focus on. Correlation is a measure of how closely related two sets of data are. The higher the correlation, the closer the data sets are to forming a straight line. And we can represent correlation both visually and symbolically. So if I took these points here, and I notice if I said these were my scatter plot of data, they almost perfectly form a straight line, which means that they would have a very high correlation. However, if I took these points, which are all very far spread out, I would say that this has very low correlation because they're not very close to having a straight line. So an example of this would be like these values right here, or these graphs right here. You'll notice that these points are all very closely grouped together, and they form not quite a straight line, but pretty close to a straight line. So these would have a strong correlation. And you notice that they have a negative slope, so we'd say that these have a strong negative correlation. Now, if we look here, these are also negative, but they're not very close to a straight line, so we're going to say that these have a weak negative correlation. They slope down, but they're not very close to forming a straight line. The numbers aren't very, or the points aren't very close together, so we're not going to say that these have a very strong correlation at all. Then down here, you'll notice that on these we're sloping up, but once again they're kind of not very close together, so we're going to call this a weak positive correlation. And then these points are all pretty close together and trending upwards, so we're going to call these a strong positive correlation. All right. Now, over here, these numbers, well, they don't really seem to slope in any direction. I could draw a line through here down or a line up through here. I don't really know. Not really know exactly what we'd call this. They don't really correlate at all. So we're actually going to call this one, we're going to say that this one has no correlation, because they don't really seem to correlate at all. They don't form any sort of line. Now these points down here, not only do they form a straight line, but they are perfectly in a straight line. So this is what we would call a perfect correlation. And because they're trending upwards, we call this a perfect positive correlation. All right, so these are all our different types of correlation. We could also have a perfect negative correlation. A perfect negative would just be dots in a straight line going down, but doesn't really make a difference. You get the idea. Now these numbers up here are important. These R's. What these R's are called is R is what's called, well, if it'll load, R is what's called the correlation coefficient. All right, it's a vocab word you need to know. Okay, and the closer the absolute value of R is to 1, the better the correlation. A correlation of 1 or -1 means that the data forms a perfectly straight line. So if we go back to the previous page, you can see that I have an R of 1 here, and these data points all formed a perfectly straight line. Okay, if R is positive, the data has a positive slope, and if R is negative, the data has a negative slope. So if we look here, this has an R of -0.9. So it's telling us the line slopes down, and 0.9 means it's really close to being a straight line, so we call it, a strong negative. Alternatively, this R is a -0.5, which means that it's got a correlation. It's not 0, it has some sort of correlation, and it's negative, it's sloping down. But our dots aren't really all that close together, so it's not going to be a very strong correlation. Similarly, I've got a +0.5 and a +0.9 here. Now we notice R is 0 here, which means there's no correlation at all. If R is really close to 0, there's not going to be much correlation. So we're going to say, for the intents and purposes of this class, that if R is greater than 0.8, or R is less than -0.8, we're going to call these strong correlations. Everything else is sort of weak, but anything that's above 0.8 or less than -0.8, we're going to call those strong correlations. So let's look at an example here. Example 2 says, determine the correlation of each set of data. So I'm asking, is it strong, weak, or no correlation at all? So let's look at A here. Well, it has some sort of correlation. We could see if we move this way that our data is kind of sloping down. But our dots are very far apart. So we're going to call this one a weak negative correlation. Because it has some correlation. They all kind of trend in the same direction. But they're not very close to forming a straight line, so that's a weak negative. B doesn't give us a graph, but it says R is 0.87. So our correlation coefficient is 0.87. That's pretty close to 1. We've said that anything above 0.8 is strong, so we're going to call this a strong positive correlation. If I was to draw a picture of my data, ugh, that's terrible. Here, let's do a little bit better job of drawing pictures. If I was to draw a picture of this data, if that's my x-axis, this is my y-axis. If I was to use my r as 0.87, I'd say what these are not totally in line, but they're pretty close to forming a straight line. All right, we use the fact that we know our correlation coefficient, our r, is close to 1. That tells us that we form a pretty close to a straight line. Now down here, looking at C, well, these numbers are all over the place. So I could draw a line trending upwards, I could draw a line trending downwards, I could do all sorts of stuff. So this one has, oh, where's it at? Well, I seem to have lost my little typed out one, so we're just going to write it in. This one has no correlation. So whenever my numbers are kind of all over the place like that, whenever my points are all over the place, that is a no correlation. So we've got a weak negative, a strong positive, and then no correlation. All right, so our final thing we're going to talk about is a line of best fit. So a line of best fit is a line that can be used to model the data. The line's drawn to be as close to the middle of the data as possible. We want it to fit, if we think of our word here, okay, we want it to fit the data as best as it possibly can. All right, now it's very rarely going to be perfect, but we want it to be as close as it can to modeling the relationship we see with the data. And we can use it to predict data values. And the correlation coefficient is going to tell us how accurate the line is. So if we have like a high correlation coefficient, like a 0.96, that would tell us the line is very accurate. So let's say I gave you some points. I just said, okay, here's some points. All right, and I want to draw a line of best fit for these points. Well, my line isn't going to pass through every single one of those points. In fact, my line might not pass through any of those points. But we want it to be as close to the data as possible. So I'm going to just draw one through like this. Now, does it hit every single one of the points? No. Does it hit even, it only hits like one or two of the points. But that's okay. We just want it to fit the data as best as possible. And mine's maybe not that great. I maybe want to grab it and move it a little bit more into the center there. That's probably a better line of best fit. All right. Now, in class, we're going to show you how to use a calculator to come up with an equation for your line of best fit and how to more accurately draw a line of best fit. But I just want you to get from this video what a line of best fit is. It's just a line that tries to model the data as best as it can. So, example 3, I've got this scatter plot over here. And I've got the year from 1988 to 2000. And I want to know the percentage of household, and then over here we've got the percentage of households with cable TV. So, you can see that we've got a scatter plot drawn, and then we have a line of best fit drawn. And you can tell just from looking at it that this is a pretty accurate line of best fit because the dots are all pretty close to the line. But if we look at the question, it says the line of best fit has an R of 0.9. Is the line very accurate? Well, 0.9 is pretty close to 1, in which case we're going to say, yes, this is an accurate line, right? The closer R is to 1 or -1, the more accurate the line is. Now part B says use the line of best fit to predict the percentage of households with cable in 2000. All right, now obviously this is old, outdated data, but whatever. So we're going to notice that there is no dot for 2000. So all we're going to do is we're going to go over this line. We're going to use our line of best fit. We're going to go up, and we're going to see that right there is where the line predicts our data point is going to be. It's at 72, so we're going to say that our prediction is that 72% of houses will have cable TV in 2000. So you can see how we decide whether a line is accurate. We kind of just eyeball it, just look at it, but we can also use the correlation coefficient if we know that. And then also, we can use that line of best fit to predict values of information that we don't know. So we just kind of go to see where does it fall on that line. So tonight's try it problem is to use this data plot here, this scatter plot, saying weeks of practice compared to words per minute. You answer the following two questions. Would r equals 0.75 be appropriate for this graph? So look at how accurate you think this graph looks and tell me is 0.75 pretty good. And then also, use the line of best fit to predict the number of words per minute after 8 weeks of practice.